In today's tutorial, I will be teaching you how to make Flappy Bird in Unity from scratch. This is a beginner-friendly tutorial, so I will be explaining everything, including how to install Unity, navigate the editor, write some code, and a bunch of stuff in between. I've added the timestamps to the bottom of the video, so use those if you're already familiar with some of the concepts we'll be exploring. The source code and sprite source files will be available to download for my Patreon members. A huge thank you to Patrick, who became my first paid Patreon member. You're the best. If you would like to support the channel and keep me creating useful Unity things, the link will be in the description. Anyway, let's jump right in. Head over to unity.com and click the download button. From this page, you can hit the download button again, and this will download the Unity Hub. The Unity Hub is an application that acts as the central point for everything Unity on your computer. From it, you can download different Unity editor versions, create new projects, and view or manage all of your existing projects. Go ahead and install Unity Hub. Once that's done, open it up. If you don't have a Unity account, you will need to create one, so you can click the Create Account button and enter the required details. After creating your account, you can log in. And if Unity Hub doesn't automatically pick up your login, just click the login button from there and sign in on your browser. Once you're signed in, Unity will prompt you to accept the personal license, which is okay for now. And then there will be a prompt to install the Unity editor. I'm going to go ahead and say skip installation here. And instead, we'll do the installation from the install section so that we can select what we need to get started. Click the install editor button. We'll use the recommended editor version, which at the time of making this video is Unity 6. The version number is 6000.0.32f1. If you don't have Visual Studio installed, make sure the Visual Studio community box is ticked, and untick the iOS and Android build support options. Because we're just getting started, we don't need any build support. The build support is what you'll use once you're ready to build and release your game. And once you get there, you can always add any modules you need at a later stage by going to the install section and clicking the settings wheel on your editor version and going to the add modules option. But back in our installation, we'll click continue and accept the Visual Studio terms and conditions. Then we'll just wait patiently for Unity to install itself. Once the Visual Studio installation starts, make sure to click the Continue button on the Visual Studio installer. It can hide itself behind other windows if you're not looking out for it. Once you continue with that, Visual Studio will ask you what exactly you want to install. If you scroll down a bit, you'll see an option to install support for Unity. Tick that box and hit install. It will take some time to download the files it needs and install everything. But whilst it's busy doing its installation, we can head back to Unity Hub and confirm that the editor has been installed. Now that all our installations have been completed, we can head to the Projects tab by clicking the Projects button in the left menu. At the top, let's click New Project. From here, Unity will present us with a bunch of template projects that we can use to get started. We're going to use the Universal 2D template. Whilst learning, you'll come across a lot of talk about render pipelines. Render pipelines are just different techniques used for rendering graphics. For most games, you'll want to use the Universal Render Pipeline, as it supports many different platforms and is optimized to run on lower-end hardware like mobile devices and potatoes. If you're aiming for highly realistic graphics and lighting, you'll need the high-definition render pipeline. Unity has some great documentation on their render pipelines, so if you'd like to dig a little deeper, you can take a look. I'll link the docs in the description. As a general note, I'll be referring to the Unity docs a lot. Even as an experienced developer with over 10 years of experience, I regularly reference the docs when I've forgotten something or if I'm looking for clarity. Let's get back to creating our project. Make sure to select Universal 2D. We'll name our project Flappy Bird Tutorial and untick the Unity Cloud option as we don't need to use any Unity services for this project. Hit the Create Project button. Unity will take some time to set things up for us. Okay, now take a deep breath. I know the scene looks confusing and overwhelming, but it's really easy to navigate once you understand how all the pieces fit together. Let's take a moment to get familiar with the editor, the windows, and the terminology you will be hearing throughout the rest of this tutorial. On the left of the screen, we have our hierarchy. The hierarchy shows us our currently loaded scenes and all the game objects that exist in those scenes. In Unity, a scene is a collection of game objects that make up what the player sees, as well as everything that is needed to make that scene operate. So, in the case of Flappy Bird, The main game scene will be the container for our little bird, our pipe obstacles, our ground, our camera, our lights, and anything else that needs to exist in our level. Scenes are really useful, and at any point in time, you can have multiple scenes loaded into your game. Think about large worlds with many different areas, like in Stardew Valley. It would be heavy on performance and quite difficult to manage if you loaded everything into one big scene. So instead, you can logically separate the areas into different scenes and you load only the scenes you need when you need them. Back to the Unity editor. The next window is the scene view. This is a visual representation of what is currently in our scene. We can navigate our scene by holding the right mouse click in and dragging, or by pressing the arrow keys on our keyboard. We can also zoom in and out of the scene view by scrolling our mouse wheel back and forth. There is also a tab to switch to our game view, which is the tab we'll use to test out our game. By default, Unity has a pre-created scene named Sample Scene, as we can see in the hierarchy. Inside this scene, we have a main camera game object and a global light 2D game object. I've used the term game object a lot, but what exactly is a game object? A game object is just a container, and it is made up of components that determine how it functions or what it looks like on screen. A game object represents anything that exists in our scene. It could be our camera that we use to render things, so something that we don't actually see in our scene, or our bird character or our pipe obstacles, which are things we will see in our scene. All of these are represented using game objects. On the right-hand side of our screen is our inspector. The inspector shows us what components exist within a selected game object. For example, let's click the main camera game object in the hierarchy. Then in the inspector, we'll see that our main camera game object is made up of 4 components. A transform, which determines its position, rotation, and scale within the scene. It contains a camera component, which is just a script containing some code written by Unity to tell the camera how to render the objects in our scene. It contains an audio listener component, which is another script written by Unity, which listens for sounds in the world and plays them back to the player of the game. And finally, a universal additional camera data component, which handles some internal camera data. We'll be making use of the inspector window a lot. From it, we can add and remove components, as well as modify the values the components use. Finally, we have our project view. This is where we will create any files that we need for our game. Examples of files we might need are code scripts we need to write, scenes, any image files, any audio files, etc. Okay, so I could spend hours talking about the different windows and all the little details, but honestly, I think the best way for you to learn how all of this works and fits together is to get your hands dirty. So let's jump right in and start doing the fun stuff. First things first. In our project window, let's go to the scenes folder and rename our default scene to something more fitting, like game scene. As you can see, that changes the scene name in our hierarchy. I like to place a lot of emphasis on naming things correctly. As your projects grow, if your names aren't correct, things will get very confusing very quickly. So try to stick to a good naming standard as you learn. Before we add any game objects to our scene, let's quickly clarify what you currently see in the scene view. There are 2 little icons, one representing the camera and one representing the global light. These icons are called gizmos, and they will not be visible when we start our game. They are only there to show us where our camera and lights are positioned in our scene. This makes sense because the camera and lights don't have any physical objects that the player would see, so we use gizmos to keep track of them. We can hide or show our gizmos by clicking the gizmo toggle here in the top right hand corner of the screen. Now let's add a new game object to our scene that will act as the ground for now. This is a process commonly used in game development where we use simple shapes and built-in objects to prototype our game. It's known as grayboxing, and once we're happy with our prototype, we can bring in our art assets to make things look awesome. In the hierarchy, right-click and click 2D Objects, Sprites, Square. This will add a square game object to our scene. Let's rename it to ground and reposition it close to the bottom of the screen, and we'll increase its scale to be a bit taller and cover the width of the entire screen. We can do this by selecting it, either by clicking the ground game object in the hierarchy or by clicking the ground game object in the scene view. Once it has been selected, we can change its transform values, which, if you recall, are just its position, rotation, and scale in the scene. We can change its position by holding the left click in and dragging it around the scene, or by selecting it and entering in manual transform values in the inspector. If you find that you are unable to drag it around the screen, it might be because you need to select the rect tool, which you can do by clicking this little square looking icon in the right hand corner of the scene view, or by using the T hotkey. I'll center it by using the inspector by setting its X value to 0, and then drag out the edges to increase its scale on the X and Y axis. Finally, with the ground still selected, let's change its color using the color property in the inspector. We'll change it to something a bit brown that looks more like the ground would. We can do this by selecting the ground game object and clicking the color property and selecting a new color in the color picker. Nice work! You've created your first of many game objects. Let's move on to the next step and create a placeholder for our player. Right-click in the hierarchy and select 2D objects, sprites, triangle, and rename it to player. In the inspector, next to the transform component, click the 3 little dots and hit the reset button to reset the position and rotations to 0. This will place our player placeholder directly in the middle of the scene. I'm going to rotate our player object by -90 degrees on the Z-axis so that it is facing what would be forward in our game. To do this, I'll select it, and in the inspector, I'll set the Z rotation value to -90. Now, you might be thinking, how is there a Z-axis in a 2D game? Surely there is only X and Y. But at its core, Unity is still a 3D game engine, and as such, it always works on the X, Y, and Z axes. We can see this if we click the 2D toggle in the scene view, up in the right-hand corner. And if we go back to the 2D view and experiment with the rotations, we can see how rotating around each axis affects our player placeholder. Another quick tip, you can quickly increase or decrease values in the inspector by dragging left or right on the property name. Great, so now we have a player and we have a ground game object. Let's hit the play button, which you can find at the top of our screen here, and see what it looks like. At this point, you should see our player and our ground, and you'll notice that the little camera and lighting icons have disappeared. That's because we're in our game view, and as I mentioned before, gizmos won't be displayed in the game view at all. So this is cool, but nothing is happening. Let's stop our game and get to work on making the player do something. We'll select the player game object, and in the inspector, let's click the Add Component button. Search for Rigid Body 2D and hit enter or click it. This will add a rigid body 2D component to our player game object. This component tells our player game object that it needs to be affected by physics, which means that now that our player has a rigid body 2D component, it will be affected by gravity and other forces. Let's hit the play button and see what happens. As we can see, our player now falls, but they fall forever. So we need to add some components to make the player interact with the world. Firstly, let's add a collider to the player game object. We can select it and say Add Component. Then we'll select the Circle Collider 2D. We can just offset it so that it is in the middle of our player. We do this by updating the offset X and Y values in the inspector for the Circle Collider 2D component. We'll also adjust the radius a little just to decrease the size. We're using a circle in this case because when we bring our bird character in, it will be pretty circular in shape. By adding a collider to our bird object, we've told it that if it comes into contact with another collider in the scene, it needs to perform some collision logic. But to make that work, we'll also need to add a collider to our ground. So select your ground and add a box collider 2D component to it. Let's hit play and see what happens. So this is really cool. Our bird character is active, it falls and collides with the ground. But now we need to do what most people are really scared of, and that is to write some C# code to control our player. Fear not, it's easier than everyone makes you think. Firstly, let's create a new folder for our scripts. To do that, we can right-click the Assets folder in our project window and go to Create, New Folder. We'll call our new folder Scripts, and inside the Scripts folder, right-click again and go to Create, Scripting, Mono Behavior Script. This creates a new component for us that can be attached to any game objects we create. This is very similar to the components we have already been using, such as rigid body 2D and box collider 2D. The only difference is that those scripts were written by the coders at Unity, and we're going to have to write some custom C# code to control our player. We'll call it player controller, and once Unity is done creating it for us, you can double click it to open it up in Visual Studio. Inside the script, you'll see a class called player controller that Unity created for us based on the name we gave our file. In C#, a class is like a blueprint. It describes everything an object needs to operate. In this case, the player controller class is going to describe everything our bird character needs to be controlled by the player of the game. And you'll see that it inherits from a class called monoBehavior. This monoBehavior class was created by Unity, and it is what allows for our player controller to be attached to any of our game objects. It is what makes our script a component. It provides us with some functions like start and update that we see in here. In C#, functions, also known as methods, are blocks of logic that we can call from various places. Any game object that has a monoBehavior script attached to it will call these methods in a specific order. Start is called as soon as the game starts, and update is called once per frame. Using these and other functions, we can make our game objects do pretty much anything we want. To start with, let's define a private variable of type rigidBody2D called _rigidBody. A variable is a piece of information that we can store and reuse in our class. So if our player controller class is a blueprint for how our player should work, then we can use variables to keep track of useful information, like how much force should be applied when the bird jumps, or in this case, we can use a variable to get a reference to our rigidBody2D component that we added to our player earlier. A private variable is a variable that is only accessible within this class, meaning no other component can affect it. We're going to use this variable to get a reference to the rigidBody2D component that we added to our playAGameObject earlier. To do that, let's delete the start function and instead replace it with a function called awake. This function will be called as soon as we hit the start button. It's called before the start function is called, and inside it we'll write _rigidBody equals getComponent rigidBody2D. This will look through the game object that our script is currently attached to and find the rigidBody2D component that we added to it earlier. Great. So now we know as soon as our game starts, our player controller component will grab a reference to the rigidBody2D, and we can do physics related things like adding some force to the bird when the player presses an input. In the update function, let's create an if statement. An if statement is something we can use in C# to perform an action only if a condition is met. So in this case, we only want to perform the logic inside of the curly brackets that come after the if statement if the user presses the mouse button. The if statement will check if the left mouse button was clicked during the current frame. If it was, let's reset the linear velocity of our bird. We can do that by writing rigidBody.linearVelocity y equals 10f. This will change whatever the current up velocity of our bird is to 10. The reason we put an f behind the 10 is to indicate that it is a floating point number, so a number that has a decimal place. Okay, so before we do anything else, let's clarify what exactly is going on in our script. As soon as our game starts, we get a reference to our rigidBody2D component on our bird character. Remember, the rigidBody2D component is what is responsible for handling our bird's physics. Then, in every frame of the game, we're checking if the player has pressed the left mouse button in. If they have, we reset the bird's velocity on the y-axis to 10. That means if the player hits the mouse button, the bird will jump with an upward velocity of 10. Let's save our script and head back to Unity. Let's click the playAGameObject in our hierarchy and click the Add Component button. Now search for the player controller component we just created. Because our component inherits from monoBehavior, it will appear in this list. Click it or press enter to add it to our playAGameObject. We could also drag the player controller script directly into the inspector with our playAGameObject selected, or we could drag the player controller script straight into the playAGameObject in the hierarchy. Now when we press the play button, if we click the left mouse button, the bird jumps up because each time we click, we reset its velocity in the y direction to be 10. As we can see, though, this causes the bird to jump quite high. So let's head back to our script. Instead of just reducing this value though, let's create a variable that we can use to control this value from the editor directly. This way we won't need to keep updating our code whenever we want to change the value. Let's add a new private variable called jump force. It will be of type float, meaning that it is a floating point number, allowing allowing us to give it a decimal value. We want to make sure that this variable is private because we don't want to allow other scripts we write later to affect our jump force. But as I mentioned earlier, because it's private, it won't be accessible anywhere else, even the editor. Therefore, we must add this attribute above our variable called the serialized field attribute. This way, it will show up in the Unity editor and we can make changes to it whenever we want. Finally, we'll replace our manual 10F with our jump force variable. Let's save our script with Ctrl+S and head back to Unity. Now, if we look at our player game object, we can see that it has a jump force variable that we can change as we please. Now, if we hit the start button, we can fiddle with the value of the jump force as well as the value of the gravity scale on the rigid body to get the bird's jump force feeling exactly how we want. I think a value of 5 for the jump force and a value of 1 for the gravity scale feels pretty good, but we can adjust these as we add our obstacles. The important thing to remember is that component values that we change whilst running our game will not persist after we stop the game. So we need to remember to change the values after stopping our game as well. Okay, so now that we have our player controller set up, we can move on to something a little more complicated. Let's get to creating our pipe obstacles and create the pipe obstacle spawner that will be responsible for continuously spawning pipes into our world for the player to avoid. Let's right-click in our hierarchy and create a new empty game object. Empty game objects are useful when we want to create children game objects or placeholders. We'll name this game object Obstacles. Next, let's right-click on our Obstacles game object and create a new square game object. This will create a new square object as a child of our Obstacles game object. We'll call it Top. Next, we'll make sure to select the Obstacles game object and let's reposition it over to the right of the screen, as this is where the pipe obstacles will spawn into the game from. We can use the Move tool to easily move our game object to where we want. To activate the Move tool, click this icon in the bottom of the scene view or use the W hotkey. With the Move tool active, let's drag the Obstacles game object over to the right of the screen. This will move all the children game objects along with it, including our top pipe placeholder. Next, let's select the top game object from inside our Obstacles game object. Then, with the Move tool active, let's move it up a bit so that we can scale it up to occupy more of the screen. Once we've moved it up to a point we're happy with, we can switch to the Scale tool by clicking this icon in the bottom right of the scene view or by hitting the E hotkey. Then we can drag out the handles to scale our pipe till we're happy with its size. You can fiddle with the Move and Scale tools till you get a result you're happy with. I think this will work for now. It's also important to remember not to spend too much time on this because we're still in our grayboxing phase. Remember, we're going to swap these ugly looking rectangles out with some real art in a little bit. With our top game object still selected, let's hit Ctrl+D to duplicate the top pipe game object. Then with the Move tool, we'll move it down to a position we're happy with, and we'll rename the game object to Bottom. We can rename game objects by selecting them and hitting F2 or changing the name at the top of the inspector. Now, as we can see, we have a bit of an issue. Our bottom pipe is rendering behind our ground. This is not what we want, and we can fix it by updating the sort order of the pipe sprite renderer components. With the top or bottom game object selected, update the order in layer to 1. We'll need to do this for both the top and the bottom pipes. As the name suggests, this will just change the order in which these sprites are rendered. The next thing we're going to need to do is write a script that makes the obstacle game object move from right to left like this. As I'm sure you've figured out by now, this is the optical illusion in Flappy Bird. The pipes are what moves, and the bird stays centered, only moving up and down. In our scripts folder, let's add a new mono behavior script. We'll call it Obstacle Handler. We'll double click it to open it up in Visual Studio. Now what we're going to need to do in this script is update the obstacle's position every frame to move to the left. Let's start by creating a private variable to keep track of the speed at which the pipes will move. We don't need the start method, so we can go ahead and delete it. Then in the update function, we'll write transform.position plus equals vector3.left multiplied by our move speed variable multiplied by time.delta time. Let's break down what this means. We're telling our obstacle game object that each frame we want to add vector3.left to its current position. We do this with the plus equals operator. This will just move the obstacle -1 on the x-axis each frame. Then we want to multiply that by our speed variable so that we can control how fast the obstacles move. And finally, we multiply that by time.delta time. Time.deltaTime gives us the difference in time between the last frame and the current frame. Multiplying by time.deltaTime will make the speed consistent irrespective of the frame rate. Lastly, we'll add the serialized field attribute to the moveSpeed variable so that we can modify it from the editor. Let's hit save and head back to Unity. With the obstacle GameObject selected, we'll drag our obstacle handler component into the inspector. Let's hit play and see what happens. Nice. As we can see, our pipes move towards the left, but I think they're moving a bit fast. So let's stop the game, update the speed, and try again. Now that looks much better. Something we haven't done is add colliders to our top and bottom pipes. So let's add those quickly in preparation for spawning pipe obstacles endlessly. We'll select the top and bottom game objects and say add component box collider 2D. The next thing we're going to do is create a prefab from our obstacles game object. A prefab is a way to keep a copy of our game object on disk. They're great for when we want to reuse an object or if we want to reference game objects directly from our scripts, which is perfect for the obstacle spawner we're going to need to create. Let's create a folder called prefabs and drag our obstacles game object into it. Once dragged in, you'll notice that the obstacles game object in our hierarchy now turns blue to indicate that it is a prefab, and any changes we make to our prefab would reflect on our obstacle game objects in the scene. Another great benefit of this is that it really helps when grayboxing. Thinking ahead a bit, we can work with our obstacles as much as we want, and when we're ready to bring in our art assets, we could simply update our prefab and all references in our scene will be updated with our art. We'll see that happen a bit later on. Now that we have a prefab of our obstacle, we can go ahead and delete the obstacles game object from our scene, as these will be spawned from a script we're going to add next. In preparation for our spawner script, let's create an empty game object called obstacle spawner and position it to the right of the screen where our pipe obstacles used to be. We're going to use the empty game object as the reference position to spawn in our endless pipes. In our scripts folder, let's create a new mono behavior script called obstacle spawner. When it's ready, we'll double click it to open it up in Unity. We're going to need a few variables. We'll create a variable to get a reference to our obstacle prefab. It will be of type GameObject. Don't forget to add the serialized field attribute so that we can assign the value in the editor. Then we'll need a variable to determine how often we should spawn obstacles. We'll call it spawn frequency and it will be of type float. We'll set it to 3 seconds as a start. Then finally, we'll need a variable to track how much time is left until we can spawn a new obstacle. We can also delete the start method as we don't need to do anything on start. Then in our update function, we're going to create an if statement that checks if the time till the next spawn is less than or equal to 0. If it is, we want to call the instantiate method, which is used to create new game objects whilst the game is running. We'll need to pass in the reference to the obstacle prefab, as well as the position and rotation it should spawn in at. We'll use the current position and rotation of the obstacle spawner game object we created earlier. After we've spawned in our new pipe obstacle, we need to reset our time till next spawn to the spawn frequency, so that it will be another 3 seconds until a new obstacle spawns. Now, in the case where the time till next spawn is greater than 0, which is handled by our else statement, we want to decrease the time till next spawn value by the time.deltaTime, which, if you remember, is just the difference in time between the last frame and the current frame. This gives us a nice easy way to have a countdown timer for each time a new obstacle needs to spawn. Let's go over what exactly will happen real quick. At the start of the game, the update function in our obstacle spawner will check the value of the time till next spawn. Because when we created the variable, we set its value to 0, it will immediately pass this condition and spawn in a new pipe obstacle. Then it will reset the value of time till next spawn to 3 seconds and move on. When the next frame comes along, the update loop will run the condition again and check if time till next spawn is less than or equal to 0. But this time the condition will fail because we reset the time till next spawn to be 3 seconds in the last frame. So this time it will run the code within the else statement, which will simply deduct some time from the time till next spawn variable. We'll continue this over and over until the time till next spawn is less than or equal to 0. Okay, I know this looks complicated, and I often see people asking questions like, how can I remember code like this? I'm just copying and pasting what you're doing. But being able to write code like this comes with practice. I didn't magically know how to do it. I research a lot. I read a lot of Unity docs. I watch a lot of tutorials. And most importantly, I experiment. For example, there are loads of different ways to write spawners, but you have to go try a bunch of different ways to truly grasp these concepts and figure out what does and doesn't work for you. And like I said at the start, join my Discord and ask questions. Alright, let's save our script and head back to Unity. Then, with our obstacle spawner game object selected, let's drag in the obstacle spawner component. As you can see, there is a slot for our obstacle prefab, so we can go to the prefabs folder we created earlier and drag in our obstacle game object. Let's hit the play button and see what happens. Brilliant! Our obstacles spawn in every 3 seconds and things are looking good. But I do notice one small issue immediately, and that is that our pipes seem to pop in on the right hand side of the screen, which will break our immersion somewhat. So let's move our obstacle spawner game object further right so that it is off the screen entirely. Now when we start our game, we can see the pipes slide in more smoothly and don't just seem to pop up out of nowhere. The next thing we want to do is add some random Y offset to the position of our pipes to make things a bit more fun. In preparation for that, let's just open up our obstacle prefab real quick. We can do this by going to our prefabs folder and double clicking the obstacle prefab. Then with the rect tool selected, remember the T hotkey or the little rectangle in the bottom of the scene view, let's drag out the top and bottom of the pipe obstacles to make them longer. This way we won't see the end of the pipes when we spawn them higher or lower in the scene. Let's open up the obstacle spawner script again. We're going to need 2 float variables, one to keep track of the minimum Y offset and one to keep track of the maximum Y offset. In C# we can use the comma to separate variables of the same type when declaring them. This will just make things look a bit neater. Remember to serialize your variables so that you can modify them in the editor. For now we'll set a default value of 1 for the minimum and 3 for the maximum. Then in our update function, we'll create a new function variable called newPosition. A function variable is similar to the global variables we've been creating, except it is only accessible within the function that you declare it in. Because we need to set it to a value that is of type vector3, we need to use the new keyword. This is because vector3 is a struct, which is another type of object in C# that we can use to store data. It can be better for performance when used correctly. I'll link the documentation to the difference between structs and classes in the description below. Trust me, it's worth a read. Then we'll type vector3 and pass in the current x position as the first parameter. And then for the second parameter, we'll use a Unity function called random.range. This will generate us a random number between the minimum and maximum values that you provide. So in here, we'll pass in our y offset min and y offset max variables. Then in our instantiate function, we'll need to replace the transform.position with our new position variable. So now, each time we are going to spawn a new obstacle into the scene, we'll first create a new position variable with a random y offset between the min and max and set the position of the newly created obstacle to that new position. Let's hit save and start the game to see what it looks like. Now the pipes spawn in different positions and we can fiddle with our min and max offsets to set the highest and lowest spawn points for the pipes. You don't have to be too pedantic about the min and max values for now, as once we replace these placeholders with proper art, the values might change a bit anyway. Our next issue is that our pipes spawn but are never destroyed, even though we can no longer see them on the screen. This is not a good thing for performance, and more system resources will be needed for pipes that are no longer in use. Let's open up our obstacle handler script to fix that real quick. In here, let's add a variable that we'll use to keep track of a minimum x position. We'll use this to check if our pipe is still on screen. Then in our update function, we'll check if the x position of our pipe obstacle is currently less than or equal to our minimum. If so, we'll just destroy it by using the destroy function. We'll need to pass in the current game object as a parameter to the destroy function like so. Let's save our script and hit the play button. Then if we switch to our scene view whilst the game is running, we can see our pipes are destroyed once they reach the minimum x value that we specified. Now, destroying game objects is not necessarily the best way to handle this scenario, and if you would like to investigate and experiment with a better, more performant way, do some research into object pooling. Next, let's handle what happens when the player collides with anything in the world. Currently, the player will just collide with the pipe and be pushed along or stay on the ground if we fall too far. But instead, we want to make it so that the player game object should disappear on collision. So let's open up our player controller script and make use of another function provided by the monoBehavior class called onCollisionEnter2D. This function will be called whenever an object with a Collider 2D component and a Rigid Body 2D component come into contact with another game object containing a Collider 2D component. Since our player has a Collider 2D and a Rigid Body 2D, and our ground and pipes have Collider 2D components, this function will be called whenever our player collides with them. So when this function is called, we want to disable our player. We can do that by typing GameObject.setActive and passing in a parameter of false. Let's save our script and hit the play button to see what happens. As we can see, our player collides with the pipe and disappears. This is the perfect time to start working on our user interface or UI. After our player dies, we want to show them their best score and a button that lets them start the game again. To do this, we need to add a canvas game object to our scene. A canvas is a game object that is made for handling user interface. Its default settings make it so that it will overlay our screen with whatever components we put inside it. As a start, let's right-click on the hierarchy and add a UI canvas. This creates a massive canvas object for us. We can double-click it in the hierarchy to focus it and bring it into the center of the scene view. Next, let's right-click our canvas and add a UI text Mesh Pro game object. This will ask us if we want to install Mesh Pro, which we can agree to. Mesh Pro is a modern and powerful text handling solution for Unity. It's free and provides us with lots of text-based features that we'll need going forward. Let's rename the new game object to Score, and with it selected, click the little square image in the Rect Transform component. This will show us the anchor presets. Whilst holding Control, click the center top button. This will anchor our text to the topmost central point of our screen. So even if our screen resolution changes, our text will stay anchored to the top center of the screen. Then we can move it down a bit on the y-axis and center the text by clicking this little center icon in the Mesh Pro component. We'll also just change its value to 0, but in time we will update this value from code. We'll move it a bit further down to make some space for the score label. We'll add another Mesh Pro game object and call it Score Label. We'll anchor it to the top of the screen. Move it down a bit, center the text and change the value to best. Finally, let's add a UI button game object. This will add a button to our canvas. Let's rename it to Start. Expand it out, click the text game object that it has as a child, and change the text value to Start. Actually, I prefer the word Play, so let's change the name of the game object and the text to Play. Next, we'll need a script to handle interacting with our user interface. In our scripts folder, let's right-click and add a new mono-behavior script. We'll call it Menu. Double-click it to open it in Visual Studio. We can delete the start and update functions as we won't need to do anything in there for now. We're going to need a private variable that we can use to manage our player game object. We'll call it Player. It will be of type GameObject. Don't forget to add the serialized field attribute so that we can assign it in the editor. We'll need another private variable of type vector3 that will keep track of where our player should be positioned when the game is started. We'll set this to vector3.0 by default and serialize it so that we can change it later in the editor if needed. Next, let's create a public void function called onStartPressed. We're going to hook this up so that when the start button we added is pressed, it will call this function. That's why it needs to be public, so that it can be accessed from other components. Inside the onStartPressed function, we want to activate our player by calling _player.setActive and passing in true as the parameter. And we want to set the player's transform.position to the player's start position variable we created earlier. If we don't reset the player's position, they will still be on the ground when we click the start button. And finally, we want to disable our user interface so that it is hidden during gameplay. To do that, we can call GameObject.setActive with the parameter of false. Next, in our player controller game object, we need to add a variable that will keep a reference to our menu game object. We need to serialize it so that we can assign its value in the editor. Then in our onCollisionEnter2D function, we just want to write _menu.setActive with the parameter value of true. This way, when our player dies, we hide the player game object, but we show the user interface. And when we hit the play button, we show the player game object, but hide the user interface. Now in our editor, let's click the canvas game object, and to it, let's add the menu component we created earlier. With it still selected, we can drag in our player game object to the player reference slot. Next, click the play button, and on the on-click box, click the little plus button to add an event for when the button is clicked. Drag in the canvas to the GameObject slot. This will give us access to all the components on the canvas GameObject, including the menu component we created earlier. Then in the function drop-down selector, find the menu component and look for the onStartPressed function we created earlier. With that, we have successfully hooked up our button to our onStartPressed function in our menu component. On our player GameObject, let's drag in our canvas to the menu reference. And the last thing we'll do is disable our player GameObject by default. To do this, we can click this little select box in the inspector. That way, when the game starts, the player will need to hit the start button to begin playing the game instead of it starting automatically. Now, if we hit the start button, we can immediately see that there is a problem. The pipes are spawning even though the player isn't alive yet. We'll hit the play button just to test it out, and that does work, but let's fix the spawner so that it knows it shouldn't spawn obstacles if the player is not alive. Let's open up the player controller script, and to it we're going to add something called a getter. A getter is a public variable that allows external components to access the value of a variable in our class, but does not allow them to change it. This is perfect for things like tracking if the player is alive, as only the player can control that. We can create it by typing public bool is alive, and then in the curly brackets we'll type get with more curly brackets, and inside that we'll return GameObject.ActiveSelf. This will return a true or false value, also known as a boolean, indicating if the GameObject is currently active. This is a good way to tell if the player is alive or not. Next, in our obstacle spawner script, let's create a variable called player to keep track of the player GameObject's player controller component. We'll serialize it so that we can assign it in the editor. Then in our update function, we'll just add a condition to our if statement that checks if the player is alive. We can do this by typing the and symbol, ampersand, twice, followed by the player.isAlive getter we just created. So now our obstacle spawner will only spawn obstacles if the player is currently alive. Let's save our script and head back to the editor. With the obstacle spawner selected, let's drag in the player GameObject to the player slot. This will assign the player controller component from the player to the player variable we created in the obstacle spawner script. And now if we hit the play button, we see that no obstacles are spawned until the player is actually alive. Now, the next thing we need to handle is showing the score to the player. This is going to require some reorganizing of our UI structure within our canvas. The reason for this is that we want to show the current score to the player even whilst the game is running. In our current structure, we hide the entire canvas when the game starts, making it impossible to show a score whilst the game is running. So let's highlight all the current game objects in our canvas and right-click and select Create Empty Parent. We'll call this Parent Menu, as this will contain all the UI components we need for our Start and On-Death menu. Then let's right-click our canvas and add an empty game object called Game. This will be a container for all our in-game UI. Let's right-click the game object and add a new Text Mesh Pro game object. We'll call it Score, and reset its current value to 0 as well as center it. Then in our anchor presets, we'll anchor the score to the top left. However, this won't anchor it to the top left of the screen yet because our parent game object does not stretch across the entire screen. We can change that by selecting the game object and in the anchor presets, clicking the stretch option in the right hand corner. As we can see, this now stretches the game UI all the way across the screen, and our in-game score will be anchored to the top left of the screen. Let's also stretch out our menu game object and recenter our play button so that we know the anchoring will be correct and consistent for all the UI game objects. I'll also just readjust the score position so that it looks a bit neater. Next, in our player game object, we need to update the UI reference we had previously set to the canvas to reference the menu game object instead. So I'll just go ahead, select the player and drag in the menu game object. Then let's open up our menu script and add a variable called menu UI of type GameObject. Remember to serialize it so that we can assign it in the editor. And then in the onStart method, we'll just replace the line that sets the whole GameObject to be inactive with one that just updates the menu UI GameObject to be inactive. We'll save our script and back in Unity, let's select the canvas game object and drag in the menu game object to the menu UI slot. Now, if we start up our game and hit the play button, we see that the menu UI is hidden, but the player score is still visible in the top left-hand corner of our game. With our UI set up, let's think about how we can determine when the player should earn score. To do this, we can use something called a trigger collider. A trigger collider does not interact with our player's rigid body 2D, but instead it can be used to call some code when another collider comes into contact with it. We can also set it up to be invisible. To set up a trigger collider, let's open up our obstacles prefab. Then let's add an empty game object. We'll call it completed trigger. Then we'll add a box collider 2D component to it. We'll reposition the game object close to the center of the pipe obstacle. This way, when the player moves through the middle of the obstacle, they will collide with the trigger. To make this collider function as a trigger, we'll need to select the isTrigger option in the collider component properties. I'll also just do a few more adjustments to the size of the collider by clicking this Edit Collider button and dragging the handles out a bit. I'll also position it a bit closer to the back of the pipe so that the player only gets the score if they actually pass through the obstacle. Let's open up our player script so that we can start to handle this collision. Let's add a method called onTriggerEnter2D. This is another function provided to us by MonoBehavior, and it will be called when the player collides with the trigger. For now, let's add some debug. This is a really useful way to keep track of what's going on in your game. Let's type debug.log we pass the pipe. We can use this to test that our trigger is working before spending a bunch of time on the logic. Now, if we hit the play button and switch to our console window, we can see that each time we pass through an obstacle, a little message is printed to our console window, showing us the message that we entered into our script. This proves to us that our trigger is working and we can start to add more logic to it. The console window is really useful. It will show you if you have any errors, and as I've just shown, we can use it to debug what might be going on in our game. Okay, now let's head back to our player controller. We'll create a private variable called score. It will be of type int, as it will be used for a whole number. Then in our onTriggerEnter2D function, let's replace the debug line with score plus equals 1. This will add 1 to the score each time the player passes an obstacle. Now, we need a way for our user interface to read this value, so we can create another getter, similar to the isAlive getter we created earlier. Again, this is because we only want our player to be able to change the score, but we want the user interface to be able to get the current score value from the player controller. So let's create our getter by writing public int score, and inside it we'll write get return score, which will return the current score value to whatever calls this getter. Now, if we head back to our menu script, we'll realize that our menu script is becoming more of a handler for all things user interface. So let's update the class name to user interface handler. It's important to keep updating the names of things so that they remain relevant. If you look back at your code 2 weeks or 2 months later, you'll be confused as heck if your menu script is actually handling all your UI. An important note: if you change the name of a class in your script, you need to go and change the script file to match the class name. So back in the Unity editor, let's update the menu script name to user interface handler. Once Unity has updated that, let's open it up again in Visual Studio. Let's create a variable called player controller. It will be of type player controller. And let's re-add the start method. In the start method, let's write playerController equals player.getComponent playerController. This will search through the player game object to find the player controller component so that we can get the score from it. Now let's re-add the update method and create a variable of type TextMeshPro called scoreText to get a reference to the UI score TextMeshPro component. Then in the update method, we'll just set the scoreText.text value to playerController.score.toString, which accesses the getter we created in our player to keep track of the score. We need to add the toString to convert the score to a string, as that's what the TextMeshPro component expects. So to recap, all we're doing here is updating the score UI to the current player's score from code. Let's save our script and head back to Unity. Let's expand our game UI object and select the canvas, and then drag in the score game object into the score text slot. And now we can hit the play button. As we can see, whenever we pass through an obstacle, our score updates. Great. But if we die, our best score is not updated. Let's fix that. In our user interface handler, let's create a private int variable to keep track of the best score and another TextMesh Pro UGUI variable to keep a reference to the best score UI label. Then in our update function, we'll check if our current score is greater than our best score. And if it is, we'll update our best score and set the best score text to the current best score. Okay, let's save our script and head back to the Unity editor. With the menu GameObject expanded, let's select the canvas and drag our score GameObject into the best score text slot. This is a bit confusing though because we have two GameObjects named score. So let's update the name of the GameObject in the menu to best score. This will make it easier for us to know what's going on when looking back at our setup. Let's hit play and see what happens. Okay, when we die we see the best score is updated, but there is an issue. If we hit start again, our current score is still set to 2. So to fix that, let's head back into our player controller script, and in the onCollision enter 2D function, let's just reset our score to 0 when colliding with anything, which is our death condition. And now if we test it out, we can see that our best score is correctly updated and on death our score is reset to 0. It's important to note that our best score will not be saved permanently. I think persisting data is a bit more of an advanced topic, so let me know if you would like a tutorial on that. But for a quick reference, you can look up player prefs as a temporary solution. If you've gotten this far, really well done. You pretty much have a fully functioning game. I think now is a good time to talk about art. I've used a program called Sprite to create the art for our game. As I said at the start, you'll find a tutorial on how I created the art assets on my Patreon page, but for now you can go ahead and download the Sprite Atlas file, a link will be in the description. In your project window, create a new folder called Textures and drag in the Sprite Atlas file you downloaded. Then, with it selected, click the Open Sprite Editor button in the inspector. You'll notice that Unity's Sprite Editor has automatically found and outlined each of our sprites. So go through each of them and name them correctly. You can do this by clicking each sprite and entering a name for it in the bottom right hand corner. This will just make it easier to identify our sprites when replacing our gray boxes with them. When you're done, make sure to hit the apply button and you can close the sprite editor. Now if you click the little arrow next to our sprite atlas, you can see a whole bunch of little sprites that we can use in our game. Let's start by deleting our ground object in the hierarchy. Then we'll drag our ground in from our sprite atlas into the scene view. This will create a new ground game object for us with the sprite renderer using the ground sprite. Let's scale it up a bit and change the draw mode to tiled in the inspector. Then if we drag out the handle on the side, we'll see our ground sprite repeats. There is a bit of a gap between each ground tile though, so let's open up the sprite editor and bring the sides of the ground sprite in a bit so that they blend a bit better. Don't forget to hit the apply button after making your changes. Now if we close the sprite editor, we can see the ground tiles blend into each other quite nicely. Next, let's open up our obstacles prefab. Then let's drag in our top and bottom pipes. Then we'll position and scale each of them until they match what we had previously. Once we're happy, we can delete the old pipe objects, and we'll just need to add in a box collider 2D onto each of our new pipes. With that done, let's save our obstacles prefab and hit the play button to see how everything looks. And so far, I think that looks pretty damn good. Let's stop our game and update our UI sprites. Let's click the play button and drag in our play button sprite into the source image in the inspector. It's all stretched out, so let's just update the width and height to something square like 128 by 128. Then let's expand out our button game object and delete the text game object that is its child. Next, in our game UI, we'll add the little coin next to the current score. To do this, let's select our score game object and create an empty parent. We'll call it score collection. Then let's add a UI image game object as a child of the score collection. We'll name it icon. Then we'll drag in the coin sprite to the source image property in the inspector. Next, we'll update the anchoring so that the score text is on the right and the icon is on the left. We'll also just adjust the position a little so that things look a bit neater. So now let's hit the play button and that makes things look even better. Next up, let's handle our bird. The first thing I'm going to do is select the 3 bird sprites. Each bird represents a frame in the fly animation, and if I select all 3 and drag them into the hierarchy, Unity will automatically create an animation controller and animation file for them. Let's drag them in Unity will prompt us to save the animation file somewhere, so I'll go up one folder and create a new folder called Animations, and we'll name our animation file bird fly and hit the save button. Now Unity has created a new bird game object for us, and if we select it and look at the inspector, we'll see that it has a few components. Firstly, the sprite renderer with the bird01 frame as the source image, and secondly, it has an animator component with an animation controller that Unity created for us. Animation controllers are what Unity uses to play animation files like the bird fly animation file it created for us previously. Let's inspect the files Unity created for us in our animation folder. Firstly, we have the bird fly animation file. Let's double click it, then we'll expand the sprite on the left of the animation window. As we can see, each frame of the bird's fly animation is shown in the timeline on the right hand side of the screen. With the animation window still open, let's hide the player game object in the hierarchy by clicking this little eye icon on the left of the hierarchy so that we can see the bird01 game object. Now let's select the bird01 game object, and in the animation window, let's click the play button or hit the spacebar. This will play the bird fly animation in the scene view for us, which is a nice way for us to visualize what the animation is going to look like in our game. That looks pretty cool. Let's close the animation window and open up the bird01 animation controller. As we can see, this opens up a GUI that we can use to handle animation transitions in our game. By default, this animation controller has been set up to immediately transition to the bird fly animation when the game starts, which is exactly what we want. If you click the bird fly state, you can see in the inspector that the motion slot has the bird fly animation file set as its reference. Let's get back to setting up our player. This time, I don't want to delete our player game object because it is being referenced by other components in the scene, and if I delete it, I will need to go and update all the references, and that sounds like a lot of work. So instead, let's delete the bird01 game object that Unity created, and we'll handle the updates in the player game object manually. With the player game object selected, let's drag in our bird01 sprite into the sprite renderer's sprite slot. Our bird is tiny and rotated incorrectly, so let's remove the rotation on the z-axis that we added at the start, and increase the scale to about 4. If we click the little lock icon next to the scale, it will scale it up on all axes. Next, let's add an animator component. Then let's go to our animation folder and drag in the bird01 animation controller into the controller slot. Let us also decrease the size of the circle collider, as that would have also scaled up by 4 when we increased the scale. We'll reduce the scale to something tiny like 0.09 and remove the offset. Now if we hit the play button, our bird looks great, but our bird is active at the start of the game, which is pretty annoying. We could just try to remember to constantly disable it after working on it, but let's rather handle this from code so that we don't have to. We'll open up the player controller script, and in the awake function, let's write GameObject.setActive with the parameter of false. This will disable the game object as soon as the game starts up. Now we can save our script and head back to Unity. Let's hit the play button, and man, that looks pretty cool. The animations are playing well, except it's pretty hard to see our bird against the blue Unity background. So back in Sprite, I went ahead and created this background image. You can also find a download link to this in the description below. You can go ahead and drag in the file you downloaded to the textures folder, change its order and layer to -1 so it is behind everything else, then scale it up so that it fits the screen nicely. You can also fiddle with the position till you get something that you think looks quite nice. Then let's hit play and see what everything looks like. That looks way better, and we have a fully functioning game. One last thing I'd like to do is make the bird rotate downward when it's falling and rotate upward when it jumps. To do this, let's open up our player controller script. Then in the update function, let's write transform.rotation equals quaternion.euler, and in its parameters we'll pass in 0f, 0f, and then rigidbody.linearvelocity.y. This will rotate the bird on the z-axis according to its current linear velocity. Let's save our script. Now when we hit the play button, we can see the bird rotates, but it doesn't rotate very much and it's a bit too subtle. In our player controller script, let's add a new variable of type float called rotation multiplier. We'll give it a default value of 2. Then in our update function, we'll just multiply our linear velocity.y by the rotation multiplier to increase the amount of rotation that the bird gets when the player jumps or is falling. Now for the very last time, let's save our script and hit the play button. And with that change, our bird has a nice amount of rotation, and if we wanted to, we could adjust the rotation multiplier to make it rotate more or less when the player jumps or is falling. And with that, you've created your very first game in Unity. Thank you so much for watching, and I'll catch you on the next one.